Right, these are the ones that we're going to be incorporating into proofs for this unit. So we're going to be learning the theorem and its converse because you can use either of them within proofs. It just depends on what they're asking for. So the first one we're going to talk about is called the perpendicular bisector theorem. Okay? So this theorem states, and I'll talk about the visual in a second, but the theorem states that if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. Equidistant means equal distances. So if you have a point, all right, you have a perpendicular bisector, which in this picture, if you want to highlight or indicate what we're talking about here, this line right here is the perpendicular bisector, the one's going like this. We can tell it's a perpendicular bisector because it's perpendicular to the segment and it cuts it in half. Okay. If this is a perpendicular bisector, the theorem states that any point along here, you could choose point B, you could choose point D, you could pick any other point that you want along the angle bisector. Its distance from the endpoints is going to be the same on both sides. That's what the theorem says. These points along the perpendicular bisector are the same distance away from the endpoints of the segment. So it creates what shape? What kind of triangle? Isosceles triangle. That's going to come in handy when we're asked to solve using perpendicular bisectors. They may ask you to find angle measures or something. You can use the fact that it's an isosceles triangle to help guide you forward in those questions. Alright, so if you have the perpendicular bisector, then any point along here is the same distance from the endpoints. Alright, then we're going to talk about the converse. Remember what happens when you do the converse. You switch the order, right? So this one says if a point is equidistant, same word as in the original theorem. If a point is equidistant from the endpoints of a segment, so it was the conclusion from the previous statement becomes the hypothesis. If a point is equidistant from the endpoints of a segment, then that point was on the perpendicular bisector. Okay? So this picture right here, we have this line right here. We don't know if it's a perpendicular bisector yet, but when you look closer, they're saying that this point is the same distance from this endpoint as it is from this endpoint, right? So that is enough to indicate that this is indeed a perpendicular bisector. So you should notice that the pictures end up being the same, right? You have the perpendicular mark, you have the bisect marks, and you have the little isosceles triangle here. So the pictures are the same, it just depends on what they gave you. In this one, they gave you the perpendicular bisector first, then you got the isosceles triangle. And this one, you had that isosceles triangle shape first, and then you got that it was a perpendicular bisector. So that's the idea of the converse versus the regular theorem. Depends on what they give you first. Alright, does that make sense? Okay. Now before we move on to this one, I have to make a distinction between these two ideas up here, distance. So there's a difference between the distance from a point to a point and the distance from a point to a line. So for this one right here, you guys are trying to indicate the distance between 2 points. All you do is draw a straight line between them. Right? That's understood. When we're talking about the distance from point A to point B, you just draw a straight line. You don't go all wobbly or bendy or whatever. It's just a straight line from point to point. However, if I wanted to indicate the distance from this point to that line, how do I know which line to draw? Aren't there a bunch of them that you could draw to connect the point to the line? There are a lot of different options. So we need to be consistent on what we're talking about when we're referring to the distance from a point to a line. So it has to be the perpendicular segment that connects them. You can't just draw any line from the point to the segment. It has to be the perpendicular one. So whenever I'm referring to the distance from a point to a line or a segment or a side of a triangle or something, I'm talking about the perpendicular distance. Right? They're not going to use that word specifically, but you need to understand that that's what I'm talking about. Perpendicular distance. Right? That comes into play with this theorem. So this theorem says that if a point is on the bisector of an angle, then it is equidistant. It is equidistant from the sides of the angle. All right, notice what I'm comparing. I'm finding the distance from a point to a side, right? So they don't have the word perpendicular in here, but you have to make sure you take that into consideration. In this theorem, we're not just drawing any random line from B to the sides of the triangle. We have to draw perpendicular as best as you can kind of visually guess. Right? So, oh, by the way, I left this out. This is supposed to be in the picture already, and I accidentally didn't put that there. So you have that these two angles are congruent. That's your hypothesis. You already know that this is an angle bisector. If you know this is an angle bisector, these two little distances there are congruent. That's what the theorem says. They have to be perpendicular though. If you don't see these little boxes here indicating that the distances are perpendicular, then it all falls apart. Okay? And then we're going to see the converse. So if a point is in the interior of an angle, if a point in the interior of an angle is equidistant, same word again. If that point is equidistant from the sides of the angle, then that segment that we were talking about is an angle bisector. Alright, so if you see a picture and you see that these little distances here, which are perpendicular, which is what we wanted, if you see that they're the same, then you can say that the angle was bisected, because this is an angle bisector. So again, the picture should look identical after you finish filling everything out. It just depends on whether they gave you the bisect first and then you got the equal distances, or they gave you the equal distances first and then you got the angles bisected. Okay? So it depends on what they give you first, but they work the same way. Okay? Questions on those two theorems? Okay. We are going to learn how to use these in proofs in a little bit, but first we're just going to analyze these pictures. First question I have for you guys is, based on the information provided in the picture alone, can we determine if these segments are perpendicular bisectors or angle bisectors? That's our question. So when it says, is C on the perpendicular bisector, we're trying to confirm if these lines right here we're trying to see if those are perpendicular bisectors based on the information. So, what can you guys tell me about this one? What do we know? It is a bisector because it cuts the segment in half, okay? So we know that it's a bisector. What else would I need to know for it to be a perpendicular bisector? It would have to form right angles. Do I see that? No. All right, so one issue that we already have right here is that we don't have perpendicular. All right, but remember, in our picture for the theorem, what does the theorem say in order for it to be a perpendicular bisector? The theorem. That in order for this to be a perpendicular bisector, this point right here would have to be the same distance from here to here. Do you see that indicated in the picture? So they also don't have that equal distance I need from the theorem. So do I have enough information to say that this is a perpendicular bisector? No. So to answer the question that they were asking, no, it's not. I don't have enough information to confirm that it's a perpendicular bisector, so I can't say that. Well, no, it's just saying, it's a yes or no question, so you just say no. And there were two issues that was causing that. The fact that we didn't have enough information, there were two different things. All right, what about this one? What do I know based on the picture that's provided? Okay, so C is equal distances from the endpoints. Is that enough information in the picture to determine that this is a perpendicular bisector? Yes, that's what the theorem's for. The theorem that we just learned said that if a point is equal distances from the endpoints, then this segment that it's on is a perpendicular bisector. That's the whole point of the theorem. Because you guys you don't actually see this, right? You don't see that in the picture. You don't need that to know that it's a perpendicular bisector. That's what the theorem's for. to give you the minimal amount of information that you need to determine if it's a perpendicular bisector. So you can either see all the information provided, that they're perpendicular and it's bisecting, or you can just see that these are the same length and then conclude it's a perpendicular bisector. That's why the theorem is useful. Alright, so this one's yes by the theorem. Alright, what about this one? What in the picture tells me yes or no about this being a perpendicular bisector? You think it's yes? Why?
Because there's a right angle.
There's a right angle.
And then it separates like the half.
It cuts this in half. So it has the perpendicular and the bisector part. Alright, so this is yes, but it's not because of the theorem. Right? This is the definition of perpendicular bisector being indicated here. The definition of a perpendicular bisector says that it's perpendicular to and bisects the segment, which it's very clearly doing in the picture. So there's a difference between when you're using the definition of perpendicular bisector, which is where they give you all the information up front, or when you're using a theorem, which is taking a back door, using these distances instead of seeing the information already there. Yes.
Why couldn't it be equal distance also?
Oh, you mean because of this one?
Yeah.
Well, because that's not technically C,
Oh.
you could work your way through that if you wanted to, but it's a longer process than just going straight to the definition. But yeah, technically you'd have to say that this point is on the bisector, and then these are collinear, and then you can make the conclusion for C. Alright, so everybody okay with using the theorem for that part? Alright, now we're going to switch into the angle bisector one. So remember, it's very important for this one, you specifically need two things. The distances from the angle bisector to the sides need to be perpendicular. They also need to be, what? Equal. So you need both of those things. If you're missing one of them, then this is not going to work. So I'm looking at this picture here. We're trying to decide if this right here is an angle bisector. So what do I know from the picture? They are the perpendicular distances, which is what we want to focus on. But what's missing? Equal. It's not necessarily bisecting the segments, but the segments are not indicated to be congruent. So is this confirmation that it's an angle bisector? No. I don't have those congruent distances that I need for the theorem. Alright, what about this one? What do I have? Equal little segments here. But is that enough to prove that this is that I could draw an angle bisector through this? Why? What's wrong with it? These are not perpendicular distances. If they're not perpendicular distances, they're not useful. So this one would be no. Not perpendicular. Now, in case you're wondering why they need to be perpendicular, if I were to draw the exact same angle and then draw this exact same segment that they have here, but kind of tilt it a little bit, right? I didn't draw that very well, but if I were to draw the segment this way with the line tilted, see how these are still equal? The 4 and the 4 are still equal, but this point is going to kind of wobble up and down depending on how you tilt the line. So that's why it needs to be perpendicular, because it makes that constant setting where the point should be right through the middle. So because that's not perpendicular, it's not going to work for you. Right? Is that a somewhat good explanation of why it needs to be perpendicular? Alright, what about this one? Why not? This one doesn't have the perpendicular either. Alright, you could take this little V that they have at these 6's and you could tilt it like this, and the point P would drop or rise depending on how you have those segments working on the angle. So because we don't know perpendicular, we can't confirm that it's an angle bisector. So everybody okay with those? Now we're going to practice using those theorems to help us solve. This one right here does not involve either of the two theorems. I'm just using this one as a warm-up. Because what's tricky about these diagrams that we're going to see in a second is that there's a lot of information compacted into a tiny little picture. Alright, so that's what makes them super complicated. So we're going to warm up with this one, which uses stuff that we already know how to do, like triangle sum theorem and all that kind of stuff. We're going to do that here just to practice working with these compact diagrams, and then we'll transition into the other ones. Alright, so I know they're numbered 1 through 6, but you do not have to find them in that order. So, what's the first angle that stands out that might be easiest to find? 6. How would I find angle 6? We have a triangle here, right? So what theorem could I use? How could I solve for 6? What theorem would I use? Triangle sum theorem. This plus this should equal 180. I have 90 plus 40 is 30. Subtract that away, what do you get for 6? A good strategy when you have so many angles missing, when you find one, you should probably write it into the picture so you can have access to that in case you need it later. Alright, anything else that I could find? Or anything I could maybe add into the picture to help me?
Did you add, like, where that right angle that we were just sitting at, you can put a right angle on the other side?
Look for those, right? If you have one right angle, you know you have one right next to it. Okay. So with those new right angles, that gives you more information to work with. So is there another angle I could find? Angle 1. Right, angle 1 is inside this triangle right here that has a 90 and a 35. So what would angle 1 be? 55. Now I don't think this printed very well in your guys' packets, but there are little marks here. Do you see them? So that's saying that angle 1 and angle 2 are congruent. So if we know angle 1, what would angle 2 be? 55. These are both 55. Alright, what angle can I find next? Okay, I can use the triangle sum theorem again to find angle 5. That would be 35. What angle would be next?
4.
Okay, how would you find angle 4? Yeah, you can do a fan here, right? All these little angles right here add up to 180 because I know 3 of them and I'm just missing 1. I can add these 3 together and subtract that from 180 to get what's left of 4. Right, and then lastly, how can I find angle 3? 70 is right here. I have a 90, so what does that leave me for 3? So this was a good one to start with because you're kind of working through the diagram using previous information to help you find new information. This diagram is actually an illustration of the angle bisector. So you guys see how this angle was bisected? Right? See how the distances from this point to the sides of the triangle were perpendicular? Right? What can I say about this segment and this segment? I should use a different color, blue. What can I say about these two? They're the same, right? Because if this is an angle bisector, these perpendicular distances should be the same, right? That's not relevant to solving in this one, but again, there's another illustration of using that theorem within the triangle. Alright, so let's transition over to this one. This one we are going to need to use either of those two theorems to help us. At first, you guys will be able to find some of the angles using triangle sum theorem or linear pair or something. So let's do as much as we can right now and then see how we can bring in the theorem after we're kind of stuck and can't move forward. So what's one angle that I could find here? Right off the bat. Angle 3. I can use the triangle sum theorem to find angle 3 because I have these two angles already. So 90 and 25 are provided. What would that leave me for 3? If I know that angle 3 is 65, what angle could I then find? Angle 5 using what? The linear pair idea. So if this angle 65, what would that give me for angle 5? What is it? 115. Yeah, 115. There you go. Alright, so now, take a look. Can you find any other angles in this picture using triangle sum theorem or supplementary again? Do I have enough information to find either angle 1 or angle 2 right now? How about angle 7 or 8 or 6? No. Right now, we can't use the triangle sum theorem or linear pair to help us, so we're kind of stuck. That's why we're going to bring in this theorem, or the theorems that we just learned on the other page to see if we can get more momentum here. So what do you guys notice about the diagram besides the angles? Yeah. This right here is a perpendicular bisector. You guys see that? It cuts the bottom side of the triangle in half and is perpendicular to that segment. So this is a perpendicular bisector. Once you notice you have a perpendicular bisector, you want to think about that theorem and what it will tell you about the rest of the shape here. So what does the theorem say? If you have a perpendicular bisector, what do you know? The distances from the perpendicular bisector to the endpoints are going to be equal. So what could I add to the picture to indicate that? What two sides, I should have labeled them, but what two sides would be congruent? These two, right? Wouldn't those two be equal? Because this point right here is on the perpendicular bisector. They're the same distance from the endpoints. Do you see that? There are actually two other sides that are also equal. These ones? Yeah, these ones are also going to be equal. Because they're also representing the distance from the perpendicular bisector, just from a point that's a little bit lower down. Right? You could draw as many lines as you want to. Any distances from the perpendicular bisector to the endpoints are going to be equal. So now what kind of triangles do I have? I have two different isosceles triangles. What do we know about the angles of isosceles triangles? The bases are congruent. So because these are the two sides that are equal, I know that these angles are congruent for the big triangle. If you look at the whole picture, right? Everybody agree with me? And then if you look at the small triangle, this kind of shrimpy one right here, I know that these are equal as well. So I have two kind of overlapping isosceles triangles. They give me two base angles that are congruent. Right? So with this information, I have more momentum to keep going forward. So, does anybody see an angle that we can find now? Angle 1, what would the measure of angle 1 be? 25, because it's equal to this one. Okay, we find angle 6 now. This full angle right here is 45, because you add the two pieces together using the angle addition postulate. So the full angle is 45, which means this full angle is 45. So how do I find 6? You can take the 25 away from the 45 that you know the full measure is. So what would you be left with for 6? 20. Alright. Okay, you can find 8. So I know this is 115 and I know this is 20. And this obtuse triangle here on the above the isosceles triangle below it. So then what would that leave me for angle 8? I don't think it's 55. It's 45. Okay. What angle can I find next?
7.
We actually don't have enough information to find 7 right now. We can find angle 2. Alright, how would I find angle 2? Triangle sum theorem, right? We have a 25 here, a 25 here, and then this angle, you know, part of it, 65. So if you do 25 plus 25 plus 65 and subtract that from 180, that'll give you the measure of angle 2, which is 65, which means that angle 4 is 115, which means that angle 7 is 45. So you don't want to rush too fast because this right here is a perpendicular bisector, but do we have the information in the picture to say that it's also an angle bisector? Do we have the perpendicular distances drawn to the sides? No. So don't assume that just because it's a perpendicular bisector that it's also an angle bisector. Okay? You got to be careful because we don't have the information in the picture to show us the angle bisector part. So don't go straight to 7 being 45 just because 8 is. Okay, you got to work your way around using the perpendicular bisector. Right? So whenever you guys are stuck, look for a perpendicular bisector. If it's there, it'll give you isosceles triangles. Okay? Questions on that? We're going to shift the emphasis here to sides now. I have one angle that we're going to look for, but I want to focus on sides in the diagram. This one's kind of squished weird, so it's not necessarily to scale. When it says not to scale, that means that things that should be congruent may not look to be congruent. So if you have two things that are supposed to be equal, one might accidentally be longer than the other, just because it's been kind of rotated and squished funny. I tried to fix it, but it was a snapshot of a diagram that was already set, so I couldn't really change it. But with that in mind, we're just going to move forward. So again, these are in no particular order. You can find them however you want. So what do you guys notice about the picture? What's something that stands out? What's a detail about the picture that could help us solve? Which one? A to D, okay. So this right here is an angle bisector. How do I know it's an angle bisector? Yeah, because the angles are congruent, right? So this is an angle bisector because these two angles have been cut in half. They're each the same measure, which, by the way, that's one of the angles we're looking for. So can you real quickly find what the measure of GDE is? 42. So just get that out of the way. All right, so we know that they're both equal. How is that helpful? What do I know? If I have an angle bisector, what does that tell me? By the way, the angle that it's bisecting is this one right here. That's helpful to also include when you're trying to visualize it, understanding what the angle is. What does the theorem say? If you have an angle bisector, then what is? Which point? B, nope, B is on the side of the angle. I don't want that one. The theorem says that if you have a point on a an angle bisector, then that point is the same distance from the sides of the angle. That's what the theorem says. So I'm going to be using E. A is not really helpful here because we don't have any segments coming from A. So what two segments from E would be the same measure? EG and EC. These are the perpendicular distances from the angle bisector to the sides of the angle. The theorem says that these two should be equal, right? So if this is 8, how long should this be? This should also be 8. That's how you use that theorem within the picture. If you know it's an angle bisector, and you have the angle right here, which I do recommend you highlight so you can actually see the angle. The distances from the angle bisector to the sides of the triangle, the angle, as long as they're perpendicular, they're equal. So that's one of the things I was looking for. How long is EG? 8. That's one of the things I was looking for. All right. What's something else you guys notice? We did have an angle bisector. Do you notice anything else? Okay, I have right angle right here. What might that kind of help us to look for then? If you have a right angle, what's going on with the lines?
Since FG and DG are congruent, that means EG is an angle bisector.
This one here? Yep. So this segment, or ray, technically, so just keeps going. This is a perpendicular bisector to this segment right here. See how it cuts it in half and is perpendicular? So this is a perpendicular bisector. We can work with that. We have a theorem that tells us stuff. So I'll just highlight this too. This is a segment that's being bisected. What does the theorem say about perpendicular bisectors? If we have a perpendicular bisector, what do we know? What distances are equal? Besides the ones that are bisected, obviously. H, F, and what? Okay, so these two right here are the distances from the perpendicular bisector to the endpoints, right? And we know from the theorem that any distance from the line to the endpoints should be equal. So this is 10. How long is this? 10. Is that one of the things you were looking for? Were we looking for HD? Yep. Okay. All right. We're also looking for ED, which is here. Do I have any information in the picture that can help me find ED? I could use EF, right? Again, it doesn't matter whether you're below or above the line that's being bisected. any distance from this segment to the endpoints, they're going to be equal. So this is 12. How long is this one? Also 12. Any distances from the bisector out to the endpoints are going to be congruent. Doesn't matter where you draw them. Then the last question is asking for the length of FD. It's not really using the theorem, it's just kind of piecing the picture together. How do I find the length of FD? Yeah, we have two 8.9s, right? So I know the picture looks super jumbled because it had a perpendicular bisector and an angle bisector kind of interwoven into the picture. So you guys have to be really careful that you're isolating the information to see those and understand how to use the theorem to solve within that diagram. Anybody have any questions on that? Okay. Now these are the kinds of proofs we're going to be working with in this unit. This one right here on the left, this is just going to help us understand why the perpendicular bisector theorem works, right? So this theorem right here is not really using the theorem, it's showing why it works. This is more like what I'm going to expect from you guys, actually applying the theorem to help understand a different kind of question. This one right here is proving why the perpendicular bisector theorem works. Alright, so remember we were learning parallel proofs. We were trying to prove the alternate interior angles theorem. We couldn't actually use alternate interior angles in that proof. Remember, you can't say a circle is circular because it's a circle. Right, it's illogical. So this proof, we're going to be using other things like triangles to show why we know that if it's a perpendicular bisector, the two distances would be equal. Okay? So this is going to be a flashback to last unit, which was congruent triangles, by the way. Alright, so everybody do me a favor on the first two lines, if you can fit as best as you can, write both of the givens. Right, because I need to scooch down a little so I can fit the whole proof in. So everybody do me a favor, write both of the givens in the top line here, and then fill out the given, and then we'll go from there. These are two givens. They have put them into the picture already, except technically you could put this here. Right? So we know that they're perpendicular, we know that it was bisecting, right? So they put the picture down, okay? So when I saw that PM was perpendicular to AB, what was the first thing that popped in my head that I would have added to the picture? When you see perpendicular. For the perpendicular part. You did the bisect part, talk about perpendicular. You have right angles, right? So we would say that, and we're going to put them both in the same line again. So angle AM, is that a P? Yeah. AMP and BMP are right angles. So when we saw that we had two perpendicular segments, the first thing that should come to your mind is that the two angles created there are right angles. And how do I know that? Definition of perpendicular. Alright. Once we know that they are right angles, what else do we know about right angles? They're congruent to each other. So we're going to add that line as well. AMP is congruent to BMP. You guys remember what the reason for that is? Congruence. There. Yep. Right angles congruence theorem. Alright, so we've done everything that we can with that perpendicularity. Now let's go back and pick up with the bisecting. We know that it's bisecting. What mark did we put into the picture? Anybody? mark's already there, but what is it indicating? What does it tell us about the picture? Carmen, you said already. Yep. AM is congruent to BM. How do I know that those two are congruent? Definition of bisect. Okay, so I've used all of the givens. I've used up all the givens so far. So my proof is trying to show that this side right here is equal to this side right here. What root can I take to get there? How might I be able to extrapolate that those other two sides are equal? Remember, we can't actually use the perpendicular bisector theorem here. Yeah, we can add some information into the picture still to say that this triangle is congruent to this triangle, and then we can use CP/CTC to say that these two sides are equal. Right? So everybody see that? What other piece of information would I need to show that the two triangles are congruent? The reflexive right here in the middle. Right? How do I represent that in our proof? PM is congruent to PM. You don't have to switch the letters here because the corresponding sides match up. That is a reflexive property. Once you have all that information, why would the triangles be congruent? What rule? Side equals side. So we just need to say the two triangles are congruent. So let's say you name the first one as AMP. How would I name the other one? BMP. And then if the full triangles are congruent, if you zoom in, how can I say that AP is congruent to BP? Well, let me say that. This is why the perpendicular bisector theorem works. This is how they discovered it. Okay? So again, you can't use the theorem itself to prove the theorem. So we took a back kind of avenue to show why the theorem actually works. It's using the congruent triangles. Okay? However, the proofs I am more expecting from you guys is actually using the theorems to help you in different kinds of proofs. So that's this one right here. Okay? This is the type of proof I am expecting from this unit. I'm going to tell you that you have either a perpendicular bisector or an angle bisector, or give you that information in some other way. We have to figure out that it's a bisector yourself. But ultimately, I'm trying to prove that this triangle is congruent to that one. That's my goal. Using the fact that I have an perpendicular bisector in this diagram. Okay? So I filled out part of it already. We know we have a perpendicular bisector. It's right here. This one right here is a perpendicular bisector of HK. What can I get from that? I said that GH is congruent to GK. How do I know that? If all that I knew is that it was a perpendicular bisector, what allows me to say that those two are equal? What is GH and GK? What do those represent? In terms of the perpendicular bisector. It's the distances from the perpendicular bisector to the endpoints. What do we know about this? They're equal, according to the theorem that we just learned, right? So we're going to be using perpendicular bisector theorem. Because we knew it was a perpendicular bisector, they told us that already, we know that any distance from the bisector to the endpoints of the other segment are going to be equal. So those two sides are equal. What else can I say? Remember, we're trying to prove that the triangles are congruent. What's something else? Well, the right angle is not inside of the triangles that we're working with, so let's try to just narrow it down to just that, the sides within those triangles. Okay, well, yeah, we can skip there if you want to. So we have reflexive here, right? So we know that they're sharing that side, so we can say that GM is congruent to GM. It's using the reflexive property. Once I have those two pieces of information, what rule, do you think we might use to prove that these are congruent? What are our options? Side, angle, side, or side, side, side. Okay, in order for it to be side, angle, side, I would need to prove that these two angles are equal, right? Yep. But do we have any information in this picture to prove that this is also an angle bisector? Do we have the information to say that? Do we have perpendicular distances from the bisector to say that? No. So we don't have any information in this picture to say or eventually get to the conclusion that these two angles are equal. So we can't use side, angle, side. So the avenue we're going to try to take is side, side, side. So how could I say that these two sides are equal? Yes?
Because triangle K and H is
Why? You're on the right track. But you need a foundation for saying why it would be isosceles. Like if you want to put this mark here, what lets me say that those two sides are equal, or those two segments are equal? Yeah. Yeah. We're using this again. Do you guys see how these two little lines are still representing a distance from the bisector to the endpoints? You can draw these segments anywhere you want. They could be, you could extend the bisector down this way and you could draw them here. These would be equal too. It doesn't matter where you draw the lines, as long as they are connecting the angle bisector to the endpoints, they're always going to be equal. So we can say that KM, what would KM be congruent to? HM. And that's using the perpendicular bisector theorem again. Again, it's very flexible in how you can use it. As long as it's connecting the the perpendicular bisector to the endpoints, you're good. So then why would the triangles be congruent? Side, side, side. So just write down the proof statement here, exactly as it appears. And you're good. Alright, so don't hesitate to use that theorem as much as you can. It can come in handy when you have multiple different lines going from the endpoints to the actual bisector. Right? We don't have a proof on how to use the angle bisector, but I am going to make one, print it out, and give it to you guys later, because I felt like that was probably something you should practice with. So I will come up with a proof for the angle bisector theorem as well, and make sure I get that to you guys. Alright, we're going to switch a little bit. So this one's more friendly, right? It's not as complicated. So we're going to talk about a mid-segment. If you guys don't know what that is, the definition is right here. It's kind of like midpoint, but it's talking about segments this time. So a midpoint is a point in the middle of a segment, right? A mid-segment is a segment in the middle of a triangle. Okay? We actually are going to learn mid-segment again when we get to trapezoids. Do you guys know what trapezoids are? So we're going to learn mid-segments for triangles and then trapezoids a little bit later in the year. Essentially what we need to know about mid-segment is this. The mid-segment of a triangle is parallel to and half the length of the third side of the triangle. It's parallel to and half as long, or half the length, of the third side of the triangle. So if you wanted to add some information to this picture, you would want to make sure you include this, right? So you can clearly see which two sides are parallel. Obviously it's not parallel to the sides that it crosses. So these two are going to be parallel. You'll notice that these little segments here are equal because the mid-segment goes through the midpoints of the two sides of the triangle. So that's how you actually create the mid-segment. That's how it goes through the middle. It cuts it in half. And then whatever this is in measure, this is going to be half as long. So if this was 10, how long would this be? 5. If this was 20, this would be 10. If this was 6, how long would this be? 12. So you just have to make sure you're careful on whether you divide or multiply, depending on which one you're given and which one you're trying to find. So we're going to practice with that. That's really all you need to know about the mid-segment. Alright. So in this picture, JK and KL are both mid-segments, but for different sides. I'm trying to find the measure of JK, which is right here. What side is that parallel to? AC? So the side that it's parallel to, that's the one you're going to use to determine how long it is. So if this is 10, how long would JK be? 5, because it's just half. Right? And then AB, what is AB parallel to? In the picture. Right, AB and KL are parallel. This is the mid-segment. So if this is 6, how long would this be? 12. Yep, so you can either go forwards or backwards. It just depends on which one they want you to find. And again, to figure out which sides are corresponding to each other, like which one's the mid-segment of which side, you just figure out which ones are parallel to each other. Okay. This one over here, I'm given the lengths of the mid-segments, and I want to find the perimeter of the big triangle. So in order to find the perimeter of a triangle, shouldn't you know what all the side lengths are? That might be helpful. So what would the length of this side be? 14. Because you see this mid-segment right here is parallel to this one, so these ones are working together. So if this is 7, this would be 14. How long is this side? 10, because it matches up with the mid-segment that's 5, so they're parallel. And then what about this one? 12. So if I want the perimeter of the big triangle, what would it be? That's it. 36. Okay. Tangent. Question. How much or how big was the perimeter for the small triangle? Okay, what's the relationship between the perimeter of the triangle with the mid-segments and the perimeter of the full triangle? It's half. Right? So not only are the mid-segments individually half of the sides individually, the perimeters are also half of each other. So they have that relationship too. Okie doke. A little bit more. Alright, so these two diagrams right here, which segment would be parallel to DE? DE and BC. Which one is the mid-segment? The DE, the segment DE is the mid-segment. What's parallel to FE? BA. Okay. If AB is 21, how long is EF? 10.5. Because EF is the mid-segment, that's the shorter one in the middle here. So it's going to be half of the full length side of the triangle. If AC is 7, then how long is DF? 3.5, half again. If DE is 10.2, how long would BC be? 20.4. Because in that situation, they gave you the midpoint, so you have to make sure you multiply it to get the full length. Okay? Alright, this one over here. Alright, in the other directions, they specifically said that they were giving you mid-segments. Instead of telling you in the directions that these are mid-segments, what in the picture tells you that they are mid-segments? How do I know that these are mid-segments instead of some random lines drawn inside of the triangle? Think back to the definition of mid-segment. If I have this drawn right here, what do I need to add to the picture to show that it's actually a mid-segment instead of just randomly drawing a line? Why? Yeah, because the mid-segment's supposed to go from midpoint to midpoint. So if you don't have the little markings or the indication in the directions that it's a midpoint, then you can't assume that. But in this diagram, they gave us those little markings to show that we have midpoints. So we know these are mid-segments. So how long would XY be? Half of this, which is 7.9. Okay. What about AX, which is right here? AX is 4.6. Everybody get that? Because they weren't asking for AB. AB would be twice 4.6, but they just wanted half of that. So that's why this mid-segment and this half of the full length are going to be equal. So 4.6. And then what's the measure of YZC, which is right here? Y. Yep. Don't forget that part of the definition, right? Or the relationship between the midsegment and the side corresponding to it. These two sides need to be parallel as part of the theorem. So if we have parallel lines, we use that Z trick. These two are equal, so this is 68. Great. So they may throw that at you. You're used to using midsegment most often to find lengths. It's either half or 2 times as big. But they may ask you to find angles too. So don't forget that parallel relationship. Yeah, you can't assume that it is. Well, it might say in the directions up here. Alright, so this page is just vocabulary. We're done like solving stuff and that kind of thing. But these first 4 vocabulary words are very important. You do need to know them because we use them later. You need to be able to identify these types of lines by looking at pictures. The bottom 4 down here are just interesting tidbits of information, so I'm going to tell you that in a second. So we talked about these 2 already, right? A perpendicular bisector. Perpendicular bisector is a line that's drawn through the midpoint of a side and is also perpendicular. Okay? So make sure that you guys are able to identify and draw a perpendicular bisector if you need to. What you guys should notice that's different about this one, so you guys see how this doesn't even come from the corner? See how all the others come from corners? This one doesn't. That's what's unique about this one. We also talked about the angle bisector. It cuts through the vertex of an angle, or cuts through an angle or the vertex of a triangle, cuts it in half. These 2 are different. Have you guys ever heard of these before? Altitude or median? Anybody? Yeah? Alright, so altitude, we definitely use this a lot, especially when we get to polygons, and then area and volume and stuff like that. An altitude is a perpendicular line that is drawn from the vertex straight down to the side that's across from it. You guys remember opposite means across from? If you don't remember that, maybe write that down. When I say something's opposite from a vertex or opposite from a side, another way of thinking about that is across from. So a perpendicular line, you start at the vertex and you drop it down so it's perpendicular to the side, and that's considered an altitude. This is actually a representation of how tall a triangle is. So use altitude to determine height. And you can do that from any vertex. You could draw it from this vertex too. Right? Any vertex of a triangle, you can draw the altitude. And then this is called a median. A median goes from a vertex to connect the midpoint of the opposite side. So you go from the corner of a triangle to wherever the midpoint is across from it, and that's how you draw a median. And again, you can do this from any vertex of a triangle. Not just one, you can do it from all 3. Alright, so remember altitude, median, perpendicular bisector, and angle bisector. They will be coming up. Become useful in the future. Now these ones are just interesting things. I'm teaching them to you because I learned them when I was in geometry and I did a really cool project about them. But you guys don't have to do that, I'm just kind of mentioning it. So the orthocenter, these have a relationship to the lines we just talked about. If you were to draw every single altitude in the triangle, the spot where they all meet is called the orthocenter. So if you were to draw all 3 altitudes, they cross at the orthocenter. If you were to draw all the perpendicular bisectors, those meet at a place called the circumcenter. We're going to be talking about that we're actually going to talk about that in the circles unit. So hold on to that idea, actually. And then the last 2, if you were to draw all the medians, you get the centroid. And if you were to draw all of the angle bisectors, you would get the incenter. Right? I did a project on this one. I think the centroid is probably the most interesting of these. If you were to take any triangle or any object that's triangular and find where the centroid is, you can balance it perfectly on your finger at the centroid. It's just like the balance point of any triangle. So I actually did a project on that when I was in school. So if you would like to cut out a cardboard triangle and then find where all the medians cross and you can balance it on your finger, that would be pretty cool because that's what I did. I would bring it in, but it's kind of beat up. So that's all that we're learning today. Does anybody have any questions on the theorem? We had 3 theorems that we learned. Does anybody have any questions on those? Is there any of the vocab solving. Everybody okay with that so far? Okay. So if you guys want to start working on the homework, I think there are a couple of proofs on there. You want to give those a shot while you're in class so you can ask some questions. And then if you want to keep working on your graded assignment, that's an option too. Okay, so let me know if you guys have any questions on any of that.